I think even though you're the only one here, we're going to go ahead and get started. I'm going to be recording this, so anyone who comes in later, take a look at that. We're starting chapter 8, which is going to be some sequences and series, and I think we're going to have some probability in here. So this should prove to be a much easier chapter than chapter 7 was.
Okay.
Okay, so today our objectives are to find terms of sequences given by the nth term. We're going to look for a pattern in a sequence and try and determine a general term. We're going to convert between sigma notation and other notation for a series. And we're going to construct the terms of a recursively defined sequence. So are you familiar with the term recursive?
I'm not.
Okay, that's all right. Okay, so just a little bit about definitions and notation. You are seeing the PowerPoint, right?
Yes.
Okay. A sequence is a function where the domain is a set of consecutive positive integers beginning with 1. So an infinite sequence would just start at 1 and continue through infinity. A finite sequence is a function having for its domain a set of positive integers. They're actually countable. That makes it finite. In a formula, the function values are known as terms of the sequence. And so the function values mean the y-coordinates of the function. Which term it is are the x's. So the first term, x would be 1. Second term, x would be 2, so on and so forth. But we don't usually use x in sequences. We use n. So the nth term just means which term. So the first term in a sequence is denoted as a sub 1. The fifth term would be a sub 5. And the nth term, or the general term, as a sub n. So here we have a sequence, and a sequence is just a list of numbers. This one is infinite, I can tell by the 3 dots at the end. So looking at this, the first term is 2, so that means the x would be 1 and the y would be 2 if we were talking about ordered pairs, which we will later. The second term is 4, the third term is 8, so on and so forth. So these just happen to be powers of 2. They're multiplying by 2 each time. They're taking the first term times 2 to get 4, take that times 2, so on and so forth. So the general term might be 2 to the nth power, which means if you want to know the 10th term, you would just put in 10 for n. Did you do a little bit of this in Algebra 2 last year?
Yeah.
Okay. So if we want to find...
We had that formula.
Okay. Find the first 4 terms and the 23rd term of the sequence whose general term is given by a sub n equals negative 1 to the nth power times n squared. So if I want to find the first term, I would put in 1 for n. So a sub 1 would be negative 1 to the first power times 1 to the second power. So for both n's, they put in a 1. And they got negative 1. Plugging in 2, they got 4. Plugging in 3, they got 9. 4, they got 16, so on and so forth. So this part of the term right here, when you take negative 1 to the nth power, it makes the signs alternate. Otherwise, it's just the squares. 1 squared is 1, 2 squared is 4, so on and so forth. If I wanted to know the 23rd term, I would take negative 1 to the 23rd. And when you raise negative 1 to a power, if you raise it to an odd power, it's negative. If you raise it to an even power, it's positive. And then times 23 squared, which gives us a negative 529. So basically all the odd terms, like the first term, the third term, the 23rd term would be negative in this case. And all the even terms would be positive. So are you okay with that notation?
Yeah.
And this, when you have -1 to the nth power, just makes it an alternating sequence. Okay, given the infinite sequence, a sub 1, a sub 2, all the way up to infinity, the sum of the terms is called an infinite series. So sequence just means a list of numbers. Series means the sum of the terms. A partial sum is the sum of the first n terms. So you might say, what is the sum of the first 100 terms? A partial sum is also called a finite series or an nth partial sum. And where we use A for individual terms, N for the number of terms, we use S for the sum of the terms. So S sub N means the sum of the first N terms. So that's just a little bit of the notation that we'll be using. So for the sequence, -2, 4, -6, 8, -10, 12, -14, the sum, or S sub 1, would just be the sum of the first term, which is just -2. S sub 4 is the sum of the first 4 terms, which is 4. And S sub 5 is just the sum of the first 5 terms. So again, they're just basically notation. If you see A in a subscript, that means they want to know what that individual term is. If you see S in a subscript, they want to know the sum of that many terms. And this will be the part that is most confusing. Did you do sigma notation last year?
I don't remember, but I feel like we did.
Probably. It could be
Familiar.
the Greek letter sigma, and this is actually capital sigma. We use lowercase sigma a lot in probability, but capital sigma is comparable to the capital S in our system. So it stands for the sum. And we have numbers below and above. So the sum for K equal 1 to 4 just means that we're going to be plugging in 1 for K, and then 2 for K, and then 3 for K, and then 4 for K. And I'm going to stop at 4 because that's our top number.
Right.
So, and then the sigma means sum, and then we'll be adding those up. So you would read it. This is the sum as K goes from 1 to 4 of 2K plus 1. The letter K is called the index, and the index of the summation might be a number other than 1. So it doesn't have to start at 1. You could do K equals 2 to 8. And they might use something other than K. So if we wanted to evaluate this, the first thing we're going to do is plug in 1 for K, and we'll have 1 cubed, which they wrote down. Then 2 for K to get 2 cubed, then 3 for K, 4 for K, 5 for K. And then because it's sigma, that means summation, we're going to add all those up and we get 225. So does that notation make sense to you?
Yeah.
Okay. If we want to write in sigma notation for the sum 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, the K that you use, and sometimes you'll see it here and here instead of on top and on bottom. A lot of computer programs, it's easier for them to do this, you know, the equation.
Right.
So I know I could have said from 1 to 7. They chose to use 0 to 6, and you'll see why here in a minute. But there are a total of 7 terms. So anytime you want to know the sum of, or how many terms there are without counting them, it's always the top minus the bottom, add 1 back. So 6 minus 0 is 6. Add 1 back to get 7. There's 7 terms. If
Wait.
Excuse me?
Repeat that.
The
top.
Okay, you take the top number minus the bottom number and add 1 back. And you're adding 1 back because you're subtracting off the bottom number. So 6 minus 0 is 6. Add 1 back for 7 terms. If I would have said k equals 1 to 7, we would have done 7 minus 1 is 6. Add 1 back to get 7. So on this, they have 2 to the k power, because anything to the 0 power is 1. That's why they started with 0 instead of starting with 1. I'm going to show you another way we could have written the same sequence after we go over this, because it doesn't matter as long as when you check it, it generates the correct numbers. Okay, let me switch to my document camera. All right, so I gotta figure out how to position this under here. So those are the numbers, and they use the summation k equals 0 to 6 of 2 to the k power. So that was 2 to the 0 plus 2 to the first plus 2 to the second plus 2 to the third plus 2 to the fourth. I know I can stop when I get to 6. Another way we could have written the same one is for k to go from 1 to 7, because there's 7 terms. But I need my first term to equal 1. So if I say 2 to the k, that would be 2 to the first, which is 2. So I could just subtract 1 up here. So when I put in 1, I get 1 minus 1 is 0, 2 to the 0. And you get the same exact. So sometimes you just have to kind of plug some numbers in. It's going to be 3 minus 1. And on this one, I would go to 7 because that's my top number. Okay. So it can be a little bit confusing, but it's not too bad. Those are called explicit notations, because you can just plug any number in for k, or if we're using n's, any number in for n, and it would generate the term. But some sequences may be defined recursively or by using a recursion formula. And such a definition lists the first term. So they tell you what to start with, and then they tell you what to do to that term to generate the next term. These are generally very easy to write and use, but if you wanted the 100th term, you would have to generate the 99 that come before it. So there are some drawbacks. So again, they always have to give you the starting term, which is a sub 1 equals 5. Whoops. And you're still seeing my, I went back to the slideshow and I didn't take you with me. I finally set up another computer and I'm zoomed in just so I can see what I'm presenting.
Oh.
Yeah. It seems silly, but. Okay, so here we have a sub 1 is the first term. A sub n plus 1. When you see this, I just want you to think of the next term. because n is the term number. So if we wanted the second term, we'd have to put in 1 for n, get a sub 2. So they're saying, whenever you see this, they're saying to generate the next term, you take the current term, a sub n, and subtract 3. And they're just telling you this is only going to work for sequences that's where the first term is 1. I mean, the first term doesn't equal 1, where we start with a sub 1, rather than starting with a sub 0, or which some of them will. So the first term is given, it's 5. To find the second term means I have to put in a 1 for n. So it's going to equal 2 times a sub 1, which was given as 5. So 2 times 5 is 10. 10 minus 3 is 7. You can think of this as being the current term. So the current term is 5. So to generate the next term, you just take 2 times this term minus 3. So to generate the third term, we would take 2 times this term, which is 7, minus 3 to get 11. To get the fourth term, we would take 2 times this term, which is 11, minus 3 to get 19, so on and so forth. So this would be really easy to generate if I wanted the first 10 terms. You would just start with what was given as the first, and then you just take it times 2, subtract 3 to get the next one. Take that times 2, subtract 3 to get the next one, so on and so forth. But if I asked you what the 100th term was, that means that n would have to be 99 to get the 100th term. So you'd have to take 2 times the 99th term, which we don't know. To find the 99th term, you'd have to know the 98th term. So recursion is pretty easy to use unless you need some other term. As we get in the next units, we'll have some formulas for finding that, even if it's defined recursively. So that is it for 8.1. Like I said, I think you'll find that these are a lot easier. I think in this chapter, I went back to just one set of practice exercises, and I'll double check the due dates. I don't think I've renewed due dates for chapter 8, but these will be due next Tuesday, and the homework will be due next Wednesday.
Okay.
So if you find you have any problems with, oh, and there's Jenna. I didn't even hear you sign in. Do you want to just watch the video, or do you want me to go over the slideshow with you, Jenna? I don't.
Those if it was basically about those last